Well, I'm sad to tell you we are leaving the world of related rates, but don't be too sad. They will sure to be show up on some tests and quizzes and spirals, and you'll see them throughout the year. So let's head into our new topic today called optimization. Optimization is the ability to find the single value that will either maximize or minimize a function. The one thing that's very intriguing about this topic is you'll start to see how you can apply a lot of these problems to the real world. As an engineer, you might find yourself maximizing or minimizing to, try to maximize the volume of a pop can or the volume of a box. So in today's topics, you'll see something like maximizing volume, maybe minimizing the distance we travel, perhaps minimizing the area of a function, or, maximizing the length of something. So, with no further ado, I want you to copy these in your notebook. These are our steps, so to speak, on how to solve an optimization problem. 1, write a primary equation for the quantity to be maximized or minimized. 2, reduce the primary equation so that it is in terms of one variable. We may have to write a secondary equation with a fixed amount and sub into the primary. 3, determine the domain, which is basically just realistic possible answers. And 4, find the desired max or min values by good calculus techniques. Question 1. Find two positive numbers where the sum of the first and twice the second is 100 and the product is a maximum. Alright, so if I just slow down here, clearly I'm looking for two positive numbers. We know they're different, so the sum of the first and twice the second, so I'm just going to use x and y as my two numbers. Now recall, I need to write myself a primary and a secondary. Okay, now, the primary is the one we said in our notes there that we either want to minimize or maximize. So if I read that again, what do I want to minimize and maximize? Well, it says the product is a maximum. So I'm going to say the product of x times y is a maximum. And I'm just going to use P for product, x times y is a maximum. And that's my primary again because I want to minimize or maximize it. Now recall that your secondary should be something that is fixed in the problem. Well, they're telling us that the sum of the first plus twice the second is a fixed 100. I can't change that. So that's going to be my secondary equation. Now the goal was to write my primary equation in terms of one variable. Currently it has two, an x and a y, and I only want one. So all I do is I go to my fixed equation and I solve for the easier variable. Okay, if you want to make it more complicated and solve for the harder one, that's your choice, but common sense says solve for the easier one. To me, to get x by itself, I just have to subtract 2y. If I wanted to get y, I'd have to subtract and divide by 2, creating a fraction. So I'm going to simply solve this for x because that's easier. 100 minus 2y. Now I will substitute that into x in my primary equation. So I've got my primary equation as 100 minus 2y times y. Now let's clean that up just a touch, so I would say P equals 100y minus 2y squared. Alright, so now I've expressed my primary equation in terms of one variable. Now, the next step is to consider the domain. This particular problem is not very exciting. I'm not going to worry about the domain until we get into a real-world type situation. But there is one thing you have to really consider. The question wants you to find a maximum in this case, and that's pretty much what the whole course is about. We have to know that anytime you have a maximum, right here, right at the top, what is the one piece of calculus that's true? In our calculus world, we're all talking about slope. At the top, when I have a max, okay, anytime I have a max, or even if I had a min, Okay, at that one point in time, we know that we have a slope of 0. And that's the whole key. All right, so you've got to know, if you get one thing out of this, if you want to maximize or minimize, you are setting your derivative equal to 0. So I'm going to find p prime here. So I get 100 minus 4y. And again, I'm setting that equal to 0. Now, some of you might be concerned about, why don't I have e dy dx, e dy dt? And that's a great question. Whatever our function is in terms of is our variable that we're using. Okay, this is not a related rate with respect to time. You're not going to see any dy dt's or anything like that. Our variable is y, and we're just going with respect to y. So at this point, I'll just simply solve for y. So I've got negative 4y equals negative 100. Obviously, y equals 25. Now, you're not done there because our goal was to show that we actually have a max. Just because you get a number doesn't actually mean you're a max. So we will make a quick sign chart. We'll put our 25 on there. We'll label that p prime and p. And recall that when we do a relative, we're always plugging it into the derivative. So my cleaned up derivative is right here, 100 minus 4y. So if I plug a 1 in, I clearly get a positive, which tells me my function's increasing. If I plug a 30 in, that's 100 minus 120 is a negative, which tells me my function is decreasing. So you can see that I have created a max. I have now proved that I have a max there. So I found the variable y equals 25. To finish it, I should probably go get x. And if you recall, that original function that we wrote was x plus 2y equals 100. So I've got x plus y is 25, so that's 50 equals 100. Therefore, x equals 50. And we have completed our first optimization problem. All right, here's a great problem, one of my favorites. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing in order to reduce the farmer's expenses? So again, I'm going to slow down and draw out a picture. I've got a nice river there, and I'm going to put my fence adjacent to that river. So I don't obviously have to fence in the river here. I'm just fencing in these 3 sides. If I'm talking about the dimensions required of the least amount of fencing, I'm describing this guy's what? Hopefully you said perimeter. So I'm going to call this side x, this side y, this side is also x. And the whole key there is that you are trying to minimize your perimeter. So my primary is going to be about my perimeter, which I'm going to say is 2x plus y is my primary equation. And remember, my secondary is going to be the amount that's fixed. Well, if you go back, it says you have to have 180,000 square meters. Okay? The unit should give it away, basically. If I say square meters, I'm talking about this pasture's what? You've guessed it, area. So I'm going to say this is x times y equals 180,000. Okay, and again, that's my fixed amount for my secondary. So you'll notice my primary at the moment has 2 variables in it. I need to get it in terms of 1. In this case, if I go back to my secondary, does it actually matter who's easier to solve for, x or y? Either way, I have to divide and get a fraction. I guess you could make the case either one would be easier to solve for. I'm going to solve for x, and I'm going to say this is 180,000 over y, and I'm going to substitute that into my primary. So I've got 2 times 180,000 over y plus y equals my primary. I obviously can clean that up a little bit. I'm going to say that's 360,000 over y plus y equals my primary. Now that my primary is in terms of one function, pretty simple, I'm just going to derive it. Of course, I'm going to slow down and rewrite that. Hopefully you can see that in your head. If you can see that and don't have to write it, that's even better. So this is really that to the negative first plus y is my primary. And now I'll take my derivative. Let me recall that we are trying to find the least amount. So I am trying to minimize it. And again, that whole point of calculus is when I minimize or maximize something, my slope is equal to 0. That's why I'm setting my derivative equal to 0. I get negative 360,000 y to the negative 2, which I'm going to stick on the bottom, plus 1 equals 0. Okay. Now, some of us keep falling into this bear trap where we're taking this 1 and bringing it over and cross multiplying, and then we end up killing a solution. Remember, let's just get ourselves a common denominator. I'm going to say this is 360,000 plus, hopefully you would agree that's y squared over y squared, all over y squared equals 0. Because recall, my critical point is not only when my fraction equals 0, but also when my fraction is undefined. So when I set the top equal, I basically get y squared equals 360,000, take the square root. Hopefully you'll trust me that that is 600, or you can do the math yourself. And on the bottom I get y equals 0. Now, you'll notice I got 2 points, okay? So here's where we can talk about our domain a little bit. Keep in mind, we're trying to find values that represent the perimeter of this pasture that we're installing here. You know, I hope your good judgment would kick in and say, if you turned out to get a negative value here, clearly, you know, that's not the answer and we did something wrong. We should not get a negative value for the side of our perimeter, the length of our fence there. And hopefully your convictions will stick in there. Now, keeping common sense again, does it make sense to have anything below 0? All right, so I know my domain is actually 0 to something, so I can end my sign chart here with a 0. I know I've got 600 that I'm trying to prove as a max or a min. Put my p prime and my p here. And I'm going to plug it into my nicest derivative. Let's say I plug in a 1. Okay, that clearly falls in there. Negative 360,000 plus 1 squared over 1 squared, I hope is a very obvious negative value. And I'll plug in, 700, I get a nice positive value. And we can now see that what value did we solve for? That was when y equals 600, we have created a minimum amount of fencing. Now don't forget, we should probably go back and get the other value. My equation was x times y equals 180,000. And I can simply plug my 600 in. We get a nice x equals 300. So our dimensions are 300 by 600 that will minimize the amount of fencing this farmer needs. The next question says, consider the region enclosed by the x-axis in the curve f of x 9 minus x squared. So let's just slow down and draw that out. 9 minus x squared, of course, is an upside-down parabola shifted up 9. Okay. I know that it hits the y-axis at 9. And I know that it has roots at -3 and +3. It says, find the dimensions of the largest rectangle that can be inscribed in this region, assuming that its base lies on the x-axis. All right, so can you picture that? You are building a rectangle inside here. The only rule is the base has to sit on the x-axis. Now, there's actually an infinite number of rectangles you could draw. If everyone sat there and drew a rectangle, we'd probably all have something just slightly different. Now remember, we want the largest rectangle possible. Are you thinking you want to go really wide and not very tall? You could go very tall and not very wide, even taller and less wide. Where do you think the rectangle would fall so that its base is here and I want the largest area I can find there? All right, so I'm just going to guess at the moment, and I'm going to say maybe it's here at the point, we'll call it XY. Okay, I don't even have numbers to put on there. I'm going to call it XY, and I'm going to draw in. This is where I think the rectangle is. Maybe you drew it in a different spot. Doesn't really matter right now. Okay, that's the question. Where can you build this largest rectangle inscribed, of course means inside this region, so that the base lies on the x-axis? So basically, by me calling this the point XY, I'm really saying, let's highlight it, the distance from here to here is x, and this distance from here to here is y. All right, so now I need to come up with a primary and a secondary equation. Okay, my primary is what I want to minimize or maximize. If I'm finding the largest, okay, I'm maximizing, and I'm maximizing, hopefully you've caught the area of this function. All right, now be careful on this. If I asked you what the area of that rectangle is, what would you say? Remember, area is just length times width. Okay, I think the height here is very obvious. What would you say the base of my rectangle is? Okay, my height looks like y, but my base, if this is x and this is x, make sure you say that base is 2x times y. Okay, my secondary equation is actually a little more subtle. They actually gave it to you. Back in the directions here, they said you have f of x equals 9 minus x squared. Well, that is y equals 9 minus x squared. All right, they actually gave it to you. It's just a little subtle in the directions there. So my area function, my primary, I need to express in terms of one variable, and they told me what y was, so let's just substitute it in. So I could say my area is 2x times 9 minus x squared. Now if I left it like that, I'm inviting product rule in, so let's just use some common sense and clean that up. I would say that's 18x minus 2x cubed. Okay, now again, the one thing you're taking away tonight is anytime you want a max or a min, we know at that one special point we have a slope of 0. So I am setting a prime equal to 0. So that gets me 18 minus 6x squared equals 0. So I've got 18 equals 6x squared divided by 2. I got 3 equals x squared. Don't forget you get plus and minus radical 3. Now let's quickly go back and talk about our domain here. And, here's why it's so important. Basically, you can't have a what value. Based off where I plotted my point, I'm certainly expecting x to be a positive value, and clearly it can't be bigger than the number 3. My rectangle cannot exceed, it's inscribed in here, it cannot exceed outside of 3 there. So I think a reasonable domain here would be from 0 to 3. And why is that so important? Well, by golly, when you get to the end and you get x equals 5, that should kick in your common sense to say you did something wrong, because we know that this can't be greater than 3. Now that we've got our answers, I'm obviously going to reject my negative 1. So I've got my radical 3. I know my domain is between 0 and 3. Okay, so don't go testing some negative value. I've got my a prime and a. And probably my nicest version is right here. If I plug in, I know the square root of 4, remember, is 2, and the square root of 1 is 1, so I know that's between 1 and 2. So I could pick 2 here, I could pick 1 here. If I plug a 1 in, I get a positive. If I plug a 2 in, I get a negative. So I know I am getting a maximum value when x equals radical 3. Now just be careful on the final answer, and sometimes you'll do all this work and you'll get the multiple choice wrong because you didn't read the question. The question actually says, what are the dimensions that will lead us to this? So remember, what was the actual base? If you look at your picture, we said our area was equal to 2x times y. The base was 2 times x. So the base of this rectangle is actually 2 radical 3. Okay, and the height, well, we had that function y equals 9 minus x squared. So I would say that is 9 minus the square root of 3 squared. I would say I get a height of 6. All right, so just be careful that you actually answer the question that was asked. Well, our last question for the night. A rectangular box is to be constructed from a piece of cardboard 24 inches long and 9 inches wide by cutting equal squares from the corners and turning up the sides. I know these pictures aren't super clear, but I tried to get a snapshot for you. So basically, hopefully you can picture that this side is 24 inches and this side is 9 inches. And if you take your scissors and you kind of cut the corners out here, and you can fold it up and it will make an open box top. It says find the dimensions that will produce the box with maximum volume. Okay, so here's what you're maximizing. Your primary equation should be about volume. So let's just talk volume of a box here. Volume is length times width times height. All right, now consider this. We're taking this 24 inches, but it's not really 24 inches because it says we're cutting out equal squares from the corners. So basically, I'm going to say this square is x by x. Basically every square is x by x that I'm cutting out. So how much are you losing per side? How many x's am I losing from this side? Well, I would say that distance is now 24 minus, if I cut an x out of this corner and x out of this corner, that's 24 minus 2x. And I would say this 9 is now 9 minus 2x. Now how about the height? when you fold that up, okay, if you look at the height in this picture here, that has a height of x. It's the amount you folded it up. If you can't believe me or see it yourself, take a sheet of paper and cut the corners out and think about it. So I would say that my volume is my length, which is the 24 minus 2x, times my width, which is my 9 minus 2x, times my height. And that represents my primary equation. Now, is there anything that's fixed here? Do I need a secondary equation? Well, look at your function. It's all in terms of one variable, and that happens every now and then. I do not need a secondary equation. Okay? Now, since I want to maximize my volume, all right, I want to find a max, I want to take this derivative and set it equal to 0. Now, I don't know what you fancy. I'm going to try to avoid all that product rule nonsense, and I'm just going to take this and FOIL it all out so I don't have to deal with the product rule. So you can see I've just, like I said, I FOILed, I multiplied by x, this way I'm avoiding product rule, and I can quickly go get my v prime. So I've got 216 minus 132x plus 12x squared equals 0. Okay, and again, I'm setting that derivative equal to 0 to get a max or a min. So hopefully you can follow my work. There's my derivative, set it equal to 0. I got two values, 9 and 2. Now I do want to go back and think about the domain of my function. If this side itself is 9 inches long, and I'm going to cut two equal numbers out, clearly that number can't be greater than 9. So I'm going to say my domain is certainly positive numbers, because I'm building something. I'm going to say my domain goes from 0 to at least 9. So I've got two critical points. I've got 2. I don't even need to worry about 9. 9 doesn't make any sense. V prime and V. And this is where I'm plugging mine into, this nice cleaned up version there. Oops, I should have my 12 out front still. If I plug a 1 in, 1 minus 9 is a negative, 1 minus 2 is a negative, and a negative times a negative is a positive. If I plug a 3 in, I get a negative times a positive, which is a negative. So you can clearly see that I am maximizing when x equals 2. Now again, I just want to be clear that I actually answered the question. The question does say find the dimensions of the box that will produce the maximum volume. So I know that the height was my x, so x equals 2. I'm going to call that my width and my length. My length is 24 minus 4 is 20, and my width is 9 minus 4, which is 5. So just make sure you finally answer that question. Well, that does it for us tonight. We'll have some great problems for us to practice in class tomorrow. Have a great night.